All right. Hello, everyone, and welcome to today's webinar. My name is Eric. I'm the moderator of today's event, and you will not be hearing much from me. You will, however, be hearing more about SEEforming's creation, the SEEkey, and how it is capable of removing almost half the plastic from rigid trays. Now, we're going to be covering a lot of ground today, and we're pretty positive you're going to have some questions. We will be monitoring the Q&A throughout the event. So if you have a question, just post it in there, and we'll try to get to as many as we can. Leading today's discussion is Scott Sadowski. Scott is the co-founder of SEEforming, and he has been on a mission to reduce plastic usage for almost 30 years. And we think he's come up with one heck of a solution. Scott, how are you doing today?
I'm doing very well, Eric. Just managing too many controls, but I'm getting there. So let me get started with this. I know your time is, how do I say, important and valuable here. So the first thing that comes to question when we get to SEEkey is basically, what is SEEkey? And very simply said, what we did is it's a small retainer. Keep it that simple. But the small retainer is different in that it's injection molded. And when you injection mold a part, you get a very strong part it's something that you can snap into the tray for cover. So in a simple sense, just know that a SEEkey is a very small retainer. And we have two models. One is the MD, which you see on the right-hand side with the push button, and the other is the Mini, which is half the size of the MD, which we started with. First thing you need to know is how does SEEkey work? Simply said, we need a rigid tray for every project that we work on because SEEkey snaps into them. Now, rigid trays do an awesome job containing and securing devices in two directions. Engineers like to call it in the X and Y plane. The problem with trays, rigid trays to be precise, they don't hold the product very good in the Z direction, and that's what SEEkey solves. So we need three things. One, we need the tray. Two, we need the SEEkeys. And number three, what we do is we create mold inserts to be placed inside the geometry of the tray so that the SEEkeys can be inserted into them. You can see that on the picture that I'm circling right here. You have a device, and then over the device is the miniature retainer holding it. Down below here, you see nested trays. The beauty of SEEkey is that the SEEkeys can be inserted before the trays arrive to your facility, or they could be inserted after.
Okay, so who, sorry, Scott, I'm going to interrupt for a second. Who does load those SEEkeys in the tray? Is that,
great
the
question.
user or?
Yeah, no, great question. So SEEkeys can be loaded by, we have thermoformers that will do it, but we also have, how do I say, some MDMs and some contract manufacturers prefer to load them. And it's really a question that answers itself once you get into the system, because there are times when you should load them right away before you receive them, and there's other times you shouldn't. So it's kind of open, but it's a point of conversation later in the project. So as we pointed out, there's two SEEkeys. The first one is the MD. So this one here basically was developed first. And Mark and I came up with the idea of, what if we could just exchange a two-handed system for a simple one-finger push? It really sparks the idea from the Staples, the easy push that they had it. So with that, you have two options. Through VOC, we learned two things. Number one, pushing works. However, we have some nurses that we saw that just they want the option to either push it or slide it. So we changed the geometry to have an arrow on the end of it, because some nurses just choose to slide it across. On the Mini, we have two options as well. The slide, which is simply back and forth, whether the product you want it in or out. But we ran into a couple applications where customer just like, we like the undercut the way it is, but we really love the amount of area that you're able to cover. Can't we just lock a SEEkey in? So that's why we developed the lock. And all we needed to do is add a wedge to the back of the tray. So you can load the SEEkey in the back position, but then when you're ready, after you insert your product, you can just simply slide it forward. So the big question is why? Why did we develop SEEkey? It all originated when I was in a meeting, a medical device meeting where we had a tray with undercuts, and we had one decision to make in the meeting. And that decision was, are these undercuts too tight or are they too loose? As we talked around the table, came clearly evident that 50% of the people were just like, they thought they were too heavy or too tight. And then the other people thought they was too loose. And that's one of the biggest problem with undercuts. They're very subjective and it's a personal opinion. It was kind of funny at the time. Tim stood up and he's just like, well, we're looking for Goldilocks. It was just an aha moment to me. And as he said, we're looking for Goldilocks. And once we find her with these samples, we're going to turn around and start all over when we start the development of tooling, because the distribution of plastic is different on a production tool when you're using plug assist. Funny thing, we walk out of the meeting, I recall it vividly, and I'm just like, Tim, what are we going to do? Tim looks at me and he goes, we'll do what we always do. We'll wait until the timeline gets crunched, then we'll make a decision, and then we're going to, pressure you guys to get the tool done faster with hopes that we can still make the timeline. So that's the story. So it was really literally the aha moment where I'm just like, there's got to be a better way. So, and then the second thing we figured out, Mark and myself, is, once we very quickly figured out the security that SEEkey enables a person. But what we had an idea that this was going to be plastic reduction, but we never had an idea it would be this much. So that's why we created an analytic-driven system where we liked decisions based on, how do I say, the numbers. We have three things to look at: how much plastic we're using, what's the cost of that plastic that we're using, and then we have also figuring out, the logistics. Those are the only things we really need to worry about logistic-wise through a tray. So how does it, this is really where we're getting to the meat of it. And a lot of people are just like, how does it reduce plastic? So the first concept is very simple for a lot of people to understand. What we see on the left here is a common retainer used in a laparoscopic device. But what we can do is we exchange the plastic amount into a very small amount. You can see on this here, the retainer is using 86 grams, where on the right-hand side, you can see all we needed was 3 grams. That's huge. That's 97% plastic reduction. The other way we reduce plastic is by reducing the thickness. With trays, the devices come to us, and because the devices pretty much dictate the size of the tray, we can't really move the length and the width of the tray too much. There's some change that we can do there, but what we have a bigger impact on rigid trays is really the thickness that runs through the tray. And this thickness, what's ironic, is it's invisible to even the experts. And I can't remember how many times I've lost sodas during the course of the meetings where I'd sit with an engineer and you're just like, this is 25 mil. No, this is 30 mil. We can't determine that. So we go and we weigh it out, and then we determine who has to buy a soda for the person who got the answer right. Another way to explain that is first understand that plastic moves in 5 mil increments. And I like to call it as visible plastic and invisible plastic. So visible plastic, we have a tray sized, say, 24 by 8, and if we extend that tray 1 inch, that actually uses less plastic than if I would take the invisible plastic of a thin layer, paper thick, and stretch it across that 24-inch tray. You can see here that the paper thin plastic actually uses 11% more plastic than if adding on to an inch of plastic off the end of the tray. the advantage of SEEkey. And this is really where the rubber meets the road. But first, I want to step into what we're doing at C-Foreman and just let you understand this isn't rocket science what we're doing. In fact, after I tell you this, you're going to be walking through the grocery store and you're going to understand this concept a lot better because it's used in everyday practices and specifically in consumer packaging. On the left-hand side, you see a seven degree drafted wall cup. That's kind of the standard in the industry so they can stack these things close, the 1/4 inch. And that 1/4 inch is the same as SEEkey. But what I'm trying to get at here is typically if you're doing an undercut, you're going to be 3 degrees or less. That may look insignificant, but when you start getting into thermoforming, the ability to go from 7 to 3 is huge because you're going to be able to nest those parts together. You're going to be able to form a better product tray with the extra draft. Looks small, but it means a lot. And the other thing when you're walking through the store is look at the trays and look at the critical geometry. When you get like a clamshell or a tray cover, they're putting the geometry on the top side of the tray. And when you put geometry on the top side tray, they do it for a reason. And that reason is because that's where the most material thickness is. So jumping back quickly to 5 mil, the 5 mil increment in the industry, understand that 5 mil right away can equate to 14% plastic savings. Go to 10 mil, you're almost up to 30%. So 5 mil actually means a lot of plastic when we can do it. And what we learned with SEEkey is that every project that we had so far, a minimum we took away is 5 mil. So right there's 14% I just knocked off it. In many cases, we're moving up into the 30 mil range. And we start changing the size of it, the number can even be increased more, and you're going to see that here in a second. So when we get to medical device, they have 2 issues. And both of them are surrounded about I didn't do that up. Hold on here, sorry. They have 2 issues. Number 1, everything is centered in the tray because the device is made that way. So we have to hold on to the shaft here. When we're holding on to the shaft, what it's doing is it's positioning the critical feature into the middle of the tray. And the same thing for the contour device that's needed for a surgeon to hold on to the device. What they're doing is rounding the devices. When you round devices, what it's doing is it's moving the holder lower in the tray. Does this mean a lot? It absolutely does. And I grabbed a 3-pound deli container from the store here to make this illustration. First of all, the 3-pound. You know, a lot of people say that the trays are thicker in medical device because the weight of the product is more. Right here, it just proves that. There's a lot heavier weight in consumer trays than there is medical device. So that is an untrue statement. But the point I really want to make is location means everything when you're looking at SEEkey, just like I showed it in the deli tray to start with here. Look at the material thickness up on top, 25 thousandths. That's what SEEkey is using. Look what's happening into the middle of the tray as you thin that out. It's getting really thin. And that's what, when you start putting rounds, undercuts onto trays, that's the material you're looking. So you're trying to thicken a thin material to start with, and then it thickens back up as you see the bottom here. Here's another illustration of this. So this is an actual undercut tray on the right-hand side here. But look down where the critical feature is. It's 11 thousandths down into that area. Look at the critical feature of SEEkey. We're utilizing on a 35 thousandths tray, we're utilizing the thickest amount of material within the project. Now, what does this mean? There's a ratio that's developed here, and we're utilizing 93% of the thickness. What is the undercut within the tray using? It's utilizing 31%. What does this mean? Take a look at if I move it from 25 thousandths to 30 thousandths. I'm moving almost 4 thousandths thickness of material, closer to 5 actually. Look what's happening 25 thousandths material, or the change of 25 to 30 in this one. They're only moving and changing the material 1 thousandths of thickness. That's huge, and that's the advantage of SEEkey. If you look on the left-hand side, this is the importance of location. SEEkey at the top of the tray. SEEkey have a limited bottom into the depth that it's drawing. SEEkey, separate from the device being held for the critical plastic usage in there. Conversely, when you put an undercut into a tray, this material drawing down into the tray is thinning out all around this tray. You have to utilize and move that plastic around. We don't have much plastic to move with SEEkey, but when you do that, that's what thins the material out.
So, Scott, I got a quick question for you here. What
Okay, yeah.
happens to the sea key thinning when it's at a different level in the tray?
Yeah, good question. So basically, we're utilizing the advantage of. Let me bounce back here to one slide here. Look what happens to plastic when it starts to flatten out here. We're increasing. Do we get the full 25 thousandths? No, but we do. Even if this comes up higher, this 15 is going to increase more and more as we raise the level. So the point is, SEEkey, because of the way it's positioned and designed, you're going to gain more material and it's not going to thin out nearly as much because you have so many advantages going on here with location out of the cavity. Good question. So I want to jump and expand on this a little bit further because it played itself out in the Dickinson Meristar Award this year. And here they have a device, the capture device, and we put one SEEkey on this tray here. But as we move through this project, the brief case study of this is that they have a package, which was a pouch and a card insert that's been there for, a decade or so. And they're just like, we need to reduce cost on this. And their first, as they explained it to me, their first approach was, a rigid tray is way too much plastic and it's going to cost way too much. We can't go there. So they first moved to another pouches. But what they learned over that period is the standards have changed. The transit testing standards have changed, so they couldn't get the same pouch. And they tried thinner pouches, and it wasn't working. But when they finally got a pouch that worked, they got too thick. And once again, it got too thick. So they were pushed into rigid trays. And when they were pushed into rigid trays, what they were looking at was the material thickness was gaining too much. And that, again, was moving it out of the cost range and, allowing too much plastic for the tray itself. So the story goes, I mean, they were moving on this rigid tray for about 8 months, as I know, many different alterations. They couldn't get anything past 35,000. So the comparison, they would have had to go to 40 to be comfortable, and they were using a whole heck of a lot of undercuts, meaning 21. So once again, 35 mil was failing drop test, and it was getting way too expensive here. And what we did within 12 days is we've supplied this sample. And the first question that came back was, you're really using a 30 thousandths tray? We're up to 35 and we got to go more on the other one. And I'm just like, be assured we're using 35 thousandths. And that was the big aha moment, because that basically 40 to 30 thousandths right there is 25% less plastic. The cost savings on this project ended up being 35. As I said, we passed the first drop test. We passed every drop test that they told me about, and their assembly was faster. It got into that question that you asked, Eric. Who loads the SEEkeys? And when we got to the final package, they basically asked me, send me keys, send me trays, and let's see which, if we want them preloaded or not. And it was a simple response. Just send them to us. This is way faster than loading the key. And they came up with a number of 75%.
Wow.
And I'll say that because I see Beck and Dickinson, the people who leaded this project, is on this call right now, just for verification of how this project went and such. So
Yeah. So, and it's just the one sea key that was holding it together or holding it
yeah,
in?
I think that's a great question, and so the real transparency of this, there's actually two undercuts on this handle here. So what happened during the project? How did I get it to pass the first time? I had three SEEkeys on this when they were drop testing it, and then we were working backwards, meaning normally in the project when I was talking about the aha moment and Goldilocks, what happens is device security seems to be the last thing you're solving engineers are solving when they're developing a tray. Well, we solved it for a sample. And then what we did is work backwards. Our efforts were on how do we reduce C keys. So in this case here, we easily removed it to two, but then the customer came back, let's go to one. So it opened up the ability and how do I say, we had to rethink it. And we were started working with the thermoformer, and we ran into a situation where they said, we got to raise the thickness of the tray. And then we're just like, well, just wait a minute. And this is where analytics jumps into the thing. They said, let's raise it to 35 thousandths, then our problem solved. But because of the analytics, I was on the call right then. I just simply dumped in a different number within our analytics. And all of a sudden I'm looking at it and I'm just like, wait a minute, you're going to add 18 grams of plastic and change for a 1 gram C key. And they're just like, well, that's what we always do. So then we had to rethink, and we just went down and we thought about how to move through this project. And when we put the undercuts in, there was the other change off using analytics, because the analytics moved the nesting, basically doubled the nesting. However, the nesting didn't really play into it, because as the customer and we talked about it, the shipping was basically less than a mile down the road. So they're just like, we'll exchange how do I say, the shipping, but we'll take the plastic reduction. The other thing we did here is, okay, we have room in here for another C key. We left that space available within the tool. So if they ever change the location, they can simply add a C key and they can get the warehousing and the shipping nested out tighter.
Okay. You know, you said
So
something there that was really interesting. Um, you know, the client, or not the client, the designer saying, well, this is the way we've always done this. How often do you run into that where people just say, well, this is the way we've always done this?
yeah, it's interesting because that's the way systems are built. That's what, we're comfortable with. And when you start putting new things into it, it's like it develops fear. So that's preferred method, but uh, SEEkey's different, and that's the biggest thing we're trying to accomplish here, is just having people look at things differently and understanding the impact of them with, numbers, and not just work through the system of doing things the way they're always done. The other thing I
Right.
want to talk about here is how SEEkey improves the design. So if you look, I'll go right to the right-hand side. If you look at the picture here, look and imagine this tray. This one of the biggest issues we had was the impact of this end shot right here. But look what SEEkey's doing. Look at the beam strength we're putting in there. 1, 2, 3, 4. We got 5 beams running straight into this wall here. This was the success of how we accomplished using how do I say, beam strength to reduce plastic. Look what's happening on this side here. These undercuts cause all kinds of design problems. And this is what Mark and I see. When you're sitting here looking and trying to let plastic flow into these undercuts, you have to actually drop things down so that plastic can flow. On this one here, they have an advantage here a little bit where they can reduce the width here because the bottom is being brought up. So how are they fixing this? How many beams do they have? They basically are trying to put little shell ribs across this thing to make it work. And they got one nice thick beam here, but it does nothing for this side of the tray. And look what they're doing with the draft that I spoke about earlier. You have to have minimal draft so it can come over and touch the product itself. SEEkey improves the beams. SEEkey allows you to use draft for improved material flow, tool ejection, and logistics. SEEkey allows you to simply drop heights. We didn't like a height right here in the tray, so what we did, we just simply dropped it down to get a draw ratio we liked.
Okay. I'm going to
Let's go ahead.
stop you for 1 second again because we have a question that came in. I think it's kind of interesting. Does SEEkey work with all materials? And then there's a couple of acronyms here: PETG, HIPS, and PC.
Absolutely. I love the question. We've proved it out even on the most difficult, which is high density polyethylene. The whole key there, SEEkey is so small, the shrink ratio that engineers have to work with, it doesn't come in to impact them at all because it's very small. So we ran give us the material, we'll run it. But we know we've run the simplest, which is PETG, and the most complex, which is high density polyethylene.
Okay.
Thanks for interrupting. That's a great question.
Yes, and thank you for the question.
Here, here's what's going on here with the plastic reduction. I just put it all into summarization. You know, if we're looking at, you know, the two stages, one, we're reducing how do I say, the plastic weight of the tray, we're reducing it of the retainer. You're basically looking at a difference here, 45 grams of, you know, current proposed, and then we knock that down to basically 118 grams. This is how we look at it analytically. And this is basically, you know, what we look at from when we start a project. We look at the current method right here. We just put in inputs to give us plastic weight, give us give us an understanding how this thing's going to pack out, how much shipping and logistics you're going to have here. And then we do the same for the proposed method here of SEEkey. So when you're looking at this, what did we end up with here? We have down here is in the green basically tells you the savings. Here's the rigid tray savings. Current method versus our method, 28%. Retainer savings. Current method versus our method, 97% savings. But the real thing you're after is how much total weight did your whole package remove? And that's where we come up with 52%. This is on a retainer. This is where we're going to see the biggest impact. If you have a retainer, it's going to be hard for us not to have a major impact of 30 to 50, how do I say, percent plastic savings. Once you have the plastic savings, it's very easy to start manipulating it and put it into, you know, how many bottles of water, you know, that we just not only manufactured, or how do I say, manufactured, but also this needs to be disposed, and that's 6.4 million bottles. You can put that into barrels of oil. You can put it into metric tons of CO2. So this is really how do I say, a webinar about plastic savings, but I do want to touch on one thing, and that's the logistics savings, because a lot of times when people see our numbers, they're just like, wow, that's just salesmanship. And I want to tell you, I want to show you briefly how this 75% is possible. First of all, when you look at it, they have a retainer here and it's using up all kinds of space and it's using all kinds of plastic. When you're looking at SEEkey, that big retainer is gone. So right there is 50% gone. The other thing, when you start looking at it, when you do SEEkey, everything we nest at is a quarter inch. When you're nesting trays and they have a spacing or undercuts on them, you're automatically bumping that up to about a half inch. So we just cut it another half. Half of the retainer, half of the space within the carton itself, airspace is gone. Now you can start understanding how we can reduce the logistics of the shipping and, others say, the warehousing. This isn't an anomaly. You know, this is what took Mark and I time, because we knew we had device security right off the bat, but we needed to get, how do I say, some evidence that this plastic reduction is going to happen, and, you know, how often it's going to happen. So here you see our first 16 projects. We're up to we're over 20 now, but we're seeing the same thing. 45% we're averaging plastic savings, and then our logistic savings we're averaging 61%.
All right, so I'm going to stop you there for just a second because that was a pretty big data dump. Um, let's kind of put this into perspective. So it's reducing the weight of the packaging itself. So that's reducing the amount of money that you're spending on plastic. At the same time, it's providing the same amount of protection for the product itself. Is that correct?
You're on it. You know, there's no dispute that, I mean, challenge us. And that's the beauty of everybody that's working on this right now. They're looking at, let's challenge the system. Is it working? Is it being proved? And we're doing it. And, you know, all I can say is provide an opportunity, and everybody that's doing it right now is pleasantly surprised. Our customers are giving us a second and third project after we start working on this because the evidence is now there.
Okay.
So just briefly, I'm going to jump into the types of trays that we support here. The first one, I put a lot of time into what we're doing with device trays, and that's where it all started, is exactly what I want to do here on the left-hand side. What's really ironic here is we never saw this, and actually until the last year, is what we're doing with component handling tray actually saves more plastic than actually the device tray. You may think that that's hard to believe, but let me walk through that one quickly here. So what we figured out is with these component handling trays is when they're developed, what customers and thermoformers do is they basically say, I have this much product, this product weighs this much. I'm going to put 12 of them on a tray, and I'm going to make sure that that tray is rigid enough so that I can lift it up and it's not going to fall over on me and to get it to point A to point B. Mark and I took a different approach on this. We're just like, these trays are always on the bottom surface. What if we thin that tray out so much that it just needs to hold that tray and hold the product as it's sitting in the flat surface? And what if we put the same tray on top of it and then we lock the trays together? What will that do for us? And it does a lot here. When you're looking 59% plastic savings. So we basically, to start out, we had two 35,000 trays, tray and a cover. We basically have these 20,000 trays that are doing the same work as that plastic thickness of 70 thousandths. They're thin, they're flexible, but because we're using them in the flat surface, and as soon as we put the product in, put the next tray on, lock them together, they're as rigid, if not more rigid, than the other, tray cover application. Not only that, we can make the stack even stronger. Every time you put a tray on top of a tray and lock it together, and you can make this as tall as you want, the stack gets stronger and stronger. What's it doing? It's reducing the thickness. Not only is it reducing thickness, imagine what I just said with the stack. Because we're creating a stack, that product is being held by the top and the bottom of the tray. So we're utilizing both sides of the tray. Conversely, if you're using a tray in a cover, you're only using two sides of the four. We're using both sides. Granted, the very top tray and the very bottom tray isn't being utilized, but every tray between is touching the product. What that does is it reduces quantity. And how does the system work? The beauty of the system is we've changed a one-stage system, meaning undercuts in a tray when you're using them, when they get popped off, you're doing the removal of the undercut and the removal of the tray at the same time. But what this does is it moves it to a two-stage system. One, we're actuating the C keys to release the tray. We're not moving the tray at all. But when you do that, now there's no interference of bringing the tray separation. And then the other thing that really helps with the system is we're not moving with the product being removed. We're perpendicular to it with the locking device. What this offers, smooth tray. It reduces and organizing the product by sequence because you only can put the product in one way and you only can take it out one way. So that really helps with defect if you're looking for product within a stack. The other thing we learned as we worked through a project here is that the segregation of the project is such that where they can put multiple lots within the same box. And with that, they don't have to sit there and rely on labels to say that they have multiple lots in them. A stack equals a lot in this thing. The other thing we learned is we don't need to have bubble pack on the top side and the bottom side because everything's within the stack moving with the stack. We don't have to add that bubble wrap, to basically push trays and covers together within a stack. We really started out here with long catheters, and that was the biggest aha moment for us because when we built our first catheter, we took so much plastic out of it. It was over 50%. You could literally hold on to the two different trays, what before and after, without the device even in it. And you're just like, wow, This is a difference. You can actually be the scale in this application here. That's how much plastic we're taking out. The other thing we ran into is when I started here, I even told people, kit trays, I don't see an application for them because there's too many things within the kit tray. However, we ran into applications where SEEkey does fit and work within this. First one here is the customer wanted to make sure they had ample, how do I say, ETO coming through the Tyvek and not going through channels. So SEEkey worked very well because it doesn't use a lot of surface area and you don't have to basically channel around it. The other thing that they wanted here is basically it creates a system of removing product and organization to them. So in this case, they first wanted the implant. So they just simply removed the implant, pulled the string out of the SEEkey, so you never had to actuate this one, put it into place. And when they were ready for the needle, they simply actuated that, and it was being held within the tray itself, making sure that it's being clean, secure, and it's not being, how do I say, hanging around, so to say, touching different things. Ran into another application. This was a VOC I did basically right down the street I got a bunch of nurses together, and at the end of the session, a nurse named Angie, I'm just like, so what's your biggest pet peeve? What are you looking to solve within packaging within the OR? And she immediately said, those small little defibrillators, they're getting so small. She says, I hate hanging on to those things. I've heard that they cost $30,000 to $50,000, and we have dropped them, and we've had to dispose of them. And I kind of chuckled, and I'm just like, well, first she said, create a system where I never have to touch the device. And I chuckled, and she chuckled, and I walked away from it, and I just started thinking about it, and I came up with a serving platter for her. It just making, create a tray that she basically hangs onto the tray. And when she's ready to get rid of it, give it to the surgeon, she just simply pushes the button and the surgeon has ample finger access here just to lift the defibrillator out and put it into the person. Not only that saved her touching it, but just imagine before two people were touching it in the operating room. She's basically taken out of the package and handing it to the surgeons. Now only one person's touching it through the whole system. So there's many ways you can start looking at SEEkey and how to use it. And the final package here that I want to talk about is the, how do I say, this is a pouch product where number one, you just basically dump it into the sterile coming out of the pouch, and you got to make sure that it stays together. But the big thing you have to do there is one, keep it together, and two, typically the biggest complaint is when you're separating the tray and the retainer, what's happening is you're getting that popping action, and that's what we needed to solve mostly on this. So imagine taking a two-handed system and putting it into a one-finger press system as it sits in the floor or on the table, I apologize. So as you push the key with one hand, I can do one hand behind my back. I can actually unload this whole tray with one push of one finger. The other beauty of what's going on here is look how I'm holding the devices at the top of the tray. Typically what you're doing is you're building a hole so that when you have a tray, the product stays in the hole. By working in this manner, I can move the product to the top of the tray. When you move it to the top of the tray, what's happening is I don't need to use the extra space of a hole around it. I'm reducing surface area by having SEEkey. How do I say, it's basically all because of the removal method. I'm not getting the popping action. I can have less space.
Scott, I can also in that picture there with the thumb, that's my thumb. And as somebody who doesn't work in the medical industry, I can confirm that it's very easy to push that and open it up, even when you don't have the training to go behind it.
Yeah, I just want to add on that is what's ironic is the push feature is what got us in the system, but we now have on the Mini, we have a 2-finger pinch system. It's still one-handed, but the 2-finger pinch, how do I say pinch, is getting a lot of great reviews, especially when they're comparing it to, how do I say, retainers. What's happening with retainers is when they first looked at it and they say, SEEkey takes too long. And I said, but wait, how long is it taking you to take that retainer and actually place it in, how do I say, the sterile field to get it out of your way, that movement? When they started looking at that aspect of it, SEEkey is much quicker than a retainer even. So that's why it's getting a better review than it did when it first started. We're looking at things more objectively, I guess is what I'm trying to say. So I'm getting to the end. This is basically the last screen here, but we're basically in an unmatched position at C-forming. We're not trying to push plastic out the door. Our whole objective is basically to reduce, and SEEkey does that. And we're here to help, thermoformers, medical device manufacturers, and contract suppliers to do that. We're in the redesign, reduce, reuse think. And not only are we doing it, but we have to have proof that we're doing it. Mark and I are engineers at heart. We have the analytics. We want to prove to you that we're doing it. And not only that, after we proved it, we had to go into those 16 now plus 20 projects to prove that this is actually working. Most in this industry are in the recycle, compost, incineration. We can take a big chunk out of that plastic, specifically the plastic amount in the resin, and that's what we're here for.